All right. So, yeah, I feel that the importance of what this artificial intelligence buzz means that our society, we're supposed to kind of have an understanding of what this is and begin to create centers or communities or groups to accelerate the development of artificial intelligence. Um, Africa is still left behind, and I feel it's because maybe the competencies are not that high, or the knowledge is not that still so high, and there's a huge gap, and there are a lot of opportunities. The global markets on artificial intelligence is about it's almost hitting about 30 billion, and in Africa, we can only talk about 60 million or so market, a market of about 60 million or so. So it's a huge gap that if we decide to train people for the future, we'll be able to make benefit or use or benefit from this system. And I feel that this seminar series, my hope is that will a bit of disentangle what all this artificial intelligence buzz is and try to create for ourselves a community where we can also get ourselves involved in the global markets and participate to gain the rewards of what this market is presents to us in whole. And so for that, I'm very, very happy that today we have a very um, we have a we have one of the I'll say one of the pioneers or one of the front runners in artificial intelligence who is here with us. Muland works is a research scientist at IBM Africa Research, their research development in Africa, and this is in Kenya. And Muland himself is a Kenyan. I met him in Rwanda, and we spoke a lot about many things. And I realized he has a lot of passion for growth and development, and also wants to see a lot of changes as well. He does a lot of research in knowledge graph, in machine learning, NLP. He has a lot of things that he does. He's interested in AI for healthcare. He's interested in foundational models and density estimation for biophysical models in drug discovery as well. He did his PhD in Bonn in Germany and has been working in IBM since then after his PhD from Bonn. So he's also a lecturer at Juja at the Jomo Kenyatta University of Agriculture and Technology as well. And we are very, very happy to have Milan with us today. He's going to talk about the emergence of large language models for all. And we'll try to understand what these large language models are. So please, Milan, you can go ahead. You can share your screen if you have some slides, or if you want to go ahead, you can just go ahead.
Yeah, you can see my screen now?
Yes, we can see your screen.
Awesome, great. Thanks, Steve. It was great making collaboration when we met in Rwanda. And I mean, when you told me this series, you're gonna start this, I thought that's a good idea because as you have said with your elaborate introduction, that it's time Africa catches up with the rest of the world, because in general we're at around maybe 4 a.m. while the others woke up and are at maybe 10 a.m. So that 6-hour gap, probably we need a lot of efforts. And in the spirit of atomic habits, I think these small efforts like the one you're starting to make, and which they ultimately grow into big big things. And I think when we were in Rwanda, we were discussing about how we can make the workshop that we had there into something like a publication or something like that. And I think there's a lot of efforts that we are also making. In December, I was in Lagos in some other conference, and I was just talking about LLM still. But the idea is Africans are starting to like take the bull by the horn, like starting to organize these discussions and starting to learn these techniques and stuff like that. I think the challenge that we still have now is the challenge of data. We are traditionally, because of colonization and all that, we have lagged behind in terms of curating and preserving our data in some way or another. So in that respect, I think if we can move forward in that direction, we'll probably get into a better space. I don't need to introduce myself any further. I work with IBM Research Africa in the Kenya lab. I do research in generative models, now LLMs and stuff like that, and application in healthcare and stuff. So I chose this title because well, the title, The Emergence of Large Language Models for All, I thought that some of these topics tend to scare a lot of folks, and they tend to shy away. Oh, it's a lot of mathematics, a lot of computer science, a lot of coding, and so many people tend to like just keep off these kind of topics. But I chose specifically for all because I have a feeling that where we are headed, coding and all these concepts will be sort of like a skill, you know, like a people skill, like swimming or something. So it's time that people embrace it, and there are efforts to sort of reduce the amount of technical skills, the amount of understanding of the mathematics that lies behind it and stuff like that, so that everybody is able to play around with it. Everybody is able to sort of experiment with data. So you'll find execs, you'll find people in ops being, you know, encouraged to sort of try and play around with this. IBM just last year released what we call the Watson X. The Watson X is a platform that sort of has these generative models well defined and allows sort of like organizations and companies to have three major things: data, governance, and modeling. So you can quickly train a model, you can quickly, you know, have your data curated without having too much technical effort. And I think that's where the world is going. You know, if you think about things like ChatGPT, which is very much part of my my talk today, you know, I think all of us have at least tested a query on ChatGPT, and everybody is starting to like understand, okay, this thing works like this. If I gave it this kind of question or a prompt, it will work like this. So in that respect, I'm glad that, you know, finally everybody is, you know, can or is gonna be able to start playing around with these models. So I'll go ahead. As a bit of introduction, I had this video from Volkswagen. Sorry, it seems like it's not gonna play. Oh yeah, it plays, right. I hope you'll be able to hear the sound, but I'm just gonna skip up to around minute 13, 12. This video is what we call in-car dialogue, right? When you can talk to the car and it gives you answers. And a company called Serens it's a US company, but the arm that developed this is in Germany, in collaboration with the car manufacturer, VW is called Volkswagen, have introduced this in their car, like the new models of the Volkswagen. So I just wanted to hear the conversation and what kind of LLMs, kind of things LLMs are able to articulate in this current day and age. It will take around 3-4 minutes, and then we can proceed.
Cars like the Tiguan, Golf, Passat will stay on. And we will introduce that as soon as we have this started here with the ID7. So all the new platforms in this year will have these new assistant by AI.
Incredible. I know when we were starting out the project, I loved VW's vision of having a completely hands-free experience in a car to enable safer driving. And I know that mostly what people want to use in a car when driving are car-related functions. Do you want to start out by giving us an example of that?
Yeah, of course, sure. Let me start with the climate control. For example, by numbers, you can change the temperature in the car, like, hello, Ida.
You guys can hear the sound?
Yes, we can hear the sound.
Okay, awesome. Good. Okay.
Turn on the temperature to 74 degrees.
All right, I'm setting the temperature in the right front area to 74.0 degrees.
Wow, this is magical. So if you notice that it only changed the temperature on the passenger side.
Yeah, exactly.
We have the Saren's audio AI that detects, right? Like from the audio that you're on the passenger side, which is incredible. May I give it a try as well?
Yeah, sure. Go ahead.
So there are two ways you can access the assistant. One is keyboard, and I can also use the button on my steering wheel. So I will use the button in this case. And now, instead of saying a specific temperature, I'm just going to say in a more natural way, I am feeling cold.
Okay, warming the left front side now.
Incredible. So it just increased the temperature by 2 degrees here and making my side or the driver's side more warmer.
Yeah.
Another thing, most people through our joint research that we know use the navigation application a lot.
Yeah.
And one of the things when you're using navigation in car is you always have to enter a destination. You have to do some planning. What would be a different way of using navigation with this new AI assistant?
Yeah, may I give you a short example?
Sure.
Hello, Ida. Find me a restaurant nearby.
Search for a restaurant in the vicinity.
For
Please
example.
select a POI from the list.
Okay. So another thing would be, hello, Ida. I need medicine.
There are multiple search results. Could you please select an entry from the list?
So this is an example where you use LLM reasoning capability and you just ask for medicine, and then the LLM reasoned, and then it sent a query back to the navigation system, and the navigation system knew to pick a nearby. So can I give it a try?
Yeah,
because
sure,
one of the things that happened to me on this trip is when I came, I forgot my phone charger.
Okay.
So let me give it a try. I want to buy a phone charger.
There are multiple search results. Could you please select an entry from the list?
So as you can see that it gave me all the computer shops where I can buy. Another thing, I always like Indian cuisine, and I like to try out different cities I go. May I try and see if Ida can help me with that in Vegas? I want to eat butter chicken.
There are multiple search results. Could you please select an entry from the list?
This was great.
Yeah, but you can add on something else. Hello, Ida. Recipe of butter chicken.
According to ChatGPT, to make butter chicken, marinate chicken pieces with yolk.
I'll be coming over to your place soon.
You have to check it out with the restaurant.
This is great. Now let us switch. So this was about LLM reasoning. Let's switch to showcase some of the LLM general knowledge use cases. I know one of trips that we like to take is from LA to Vegas. And oftentimes you have young ones in the car, and it's kind of hard to keep them entertained. Can you show us how Ida can help us ease our trip?
Try. Hello, Ida. Tell me a story about dinosaurs.
According to ChatGPT, once upon a time, in a lush and ancient world, dinosaurs ruled the land. These magnificent creatures.
I know this will keep my kids entertained for a while.
Awesome.
Another example is that whenever I'm in a car,
Awesome. I think that in-car dialogue system that is powered by, well, the company has a wrapper on top of ChatGPT, where the wrapper can do things like reasoning. And you heard things like when they ask the temperature of the car, I mean the temperature to be turned off, the machine was able to understand that the voice came from the left side and turned up only the temperature on the left side. That's a bit of context, right? So it's not just a matter of understanding what he said. So there's a lot of technologies there. There's the speech understanding and decoding the speech and then understanding what was said. So it normally goes from speech, then text, then you understand the text because it was text in natural language. Then once you understand the text, the next step is about fetching the right information or the right answer for that text. And then that now goes into things like knowledge graph, what Steve was mentioning, a knowledge base or whatever it is. And then now again, coding back that into text or sound that then it can give an answer. So there's a lot of research areas there that has been brought together to be able to understand, all of them based on some mathematical models or whatever it is. But you understand that there's beyond those steps, there's the idea of context. The machine should be able to understand, okay, the right seat is the one that requires turning up the temperature. Or for example, the question on the restaurant, the context there becomes the GPS, where is the car located? And then, like what Uber does, where are you located? What are some of the restaurants around? There's a lot of computations there as well. And what I liked about this demo is that there's so many cars that has this feature, but what I like about this demo is that they have included ChatGPT. So now the assistant is able to say, okay, this source is from ChatGPT and it says X, Y, Z. But more than that, they have at least tried to ask some general domain questions beyond the reasoning questions. Like, for example, tell me a story about dinosaurs. So you can imagine what is going in the background of that and how much information has been used. Just to motivate this further, I chose to look at ChatGPT, for example, and this example I got it from the time I was trying to teach my brother some coding, programming, yeah, and at the time I was teaching Python, and I got to type this code on fetching things online, but with temporal like waiting time. Every time 30 seconds, for example, you fetch something. But how to configure that gave me a bit of a challenge. So then I was going to Stack Overflow. I was going to fetch, ask questions online. But then my brother, who was the one learning the programming, asked me, okay, what seems to be the problem? And I was like, okay, so this code on time is not able to run. And he told me, send me that code. In the next 2 minutes, he gave me a piece of code that was able to like exactly run on my situation. And for me, that was the first time I actually used ChatGPT. I had not used ChatGPT. And as much as I understood what lies behind it, I just did not appreciate to what extent this language model had become. Because if something, you can give it an error, for example, on the left side, you can see my errors and just the stack trace for my Python code. And it was able to understand the error and give me this black space code here that was able to then run. Then you understand that we are dealing with some very advanced models, right? So these are just some of the applications of LLMs and just how powerful they have become, right? So with this kind of motivation, I'm hoping that your mouth is watering, right? You're starting to think, oh, these are tools that are going to be good, because if the programmer can use it and the person in the car can use it, Maybe a doctor somewhere can use it. Maybe a patient can query for medicine somewhere. You know, so there's a plethora of applications that can be used in this kind of domain. But the question is always whether it's going to be a hype or it's going to continue to be good. And from a research perspective, I can tell you it's generally right now, it's generally a big hype. And every organization is looking on how they can jump onto the bandwagon for this. But I have to say that the hype is good, because if you think about 10 years ago, 5 years ago, if I was to walk into an office of an executive or a manager somewhere, a bank manager, or maybe you guys have a phone network called Glow network or whatever. I walk into the manager's office. I tell them, okay, you need natural language processing, or you need machine learning or AI to be able to target your advertisements to the client, right? They'll look at me like, what are you talking about? It will cost you maybe, I don't know the currency in Ghana, but if you talk about maybe dollars, I'm talking about maybe $1 million, your organization, and it's going to give you more clients. And they will look at you like, no, we are not able to do that kind of investment, right? And what is this AI anyway? They don't understand. But the fact that ChatGPT came in 2021 and gave people a chance to play around with this technology, then now the manager or what, because in projects, in AI projects, we always have the programmers, the engineers, the researchers, but the key stakeholders are the customer and the people who are going to give us the money, right? Which is the management or the team in the organization. So if once they played around with this, they now appreciate it. My work is a bit easier. If I was to walk into an office and tell them you need large language models or knowledge graphs, they'll be able to appreciate more. And know what that does? That gives us more data, gives us more funding, gives us more research into that. Now, in terms of technology in the background, I am aware, and I'm probably part of the population or the group of people that are doing this kind of research. I can tell you that it's just going to be better and bigger as we go forward. So it is a hype, and you can see this is what we call the Gartner hype cycle. In 2022, Gartner placed foundation models, which is the new name for LLMs, at the top of that cycle. So it's expected to dip, but what I project is that it's not going to dip. It's either going to go flat or go a little bit higher for a while. We are looking at a technology that's going to go for like the next 10 years before it starts dropping. Because if you think of IBM being a Fortune 500 company and they adopted this just last year, so it means that their strategy is looking at 10 years into the future. So what exactly are foundation models, or what exactly are LLMs? Foundation models are models that are able to look at huge amount of data and be able to extract representations, right, from that data, such that those representations can then now be used to be able to solve a given task. So you can see on the left here, we have like 3D signals, structured data. Structured data are things like database data, things that are in SQL or databases. Things like Excel, those are structured data. CSV format data. You can have speech, images, all forms of data. And these are pushed into a model, what we call a semi-supervised model or a self-supervised model. And that model is able to learn patterns in that data so much that those patterns it learns, it represents them into what we call a vector space. Now, Steve is a mathematician, and probably some of you are mathematicians. You probably understand what vector space is. It's a plane in an n-dimensional space where we can represent numbers, right? And a vector in that space then has a meaning, a contextual meaning, or some weights in relation to other vectors. So if, for example, I was to represent Wikipedia text, and in this Wikipedia text, I have a word like milk, I would expect the word milk, the vector space for word milk be close to that of tea, for example. Yeah. So if I was to do a similarity measure of a vector representation for milk and tea or bread, then there will be something close to each other. That is what they call distributional semantics, because this technology came from natural language processing, right? So now that's been expanded into images, into time series data, structural data, and so on and so forth. So you will hear things like protein fold, AlphaFold from Google, which is a model that is based on these techniques, but it's for molecules, right? It's able to understand a relationship between molecules, because molecules are simply structures that are related, to each other, some binding surface or whatever it is. So some of the tasks that have been traditionally applied in this area are tasks like question answering, what you have seen probably in the car. The car is more of a dialogue, but there is question answering, for example, medication answers and stuff like this, sentiment analysis. Or so often organizations produce products and they want to see how the people have enjoyed using it. For example, iPhone 15 was released 2 months ago, 3 months ago. And what they would want to do is to check if people love the screen, people love the weight of the phone, things like this. So people will give reviews on that and they will want to do that. So if I got vectors that are represented from the foundation model, I can use those vectors to be able to help me understand sentiments, right? Meanings of words, bad sentiment or good sentiment, information extraction, image captioning, and so on and so forth. I recently attended a conference, what would be arguably the topmost conference in computer science, called NeurIPS, Neural Information Processing, in December. And I thought that I would include this slide here just to show you what is going on in the research community. This conference generally captures all work in physics, computer science, mathematics, and so on and so forth. But this year's version of that conference had so much about LLMs, or large language models, which is a pointer on exactly what how people consider this to be a heavy topic and a way forward. This word cloud that you're seeing here has been drawn from the abstracts of all the papers that were submitted there. This is a conference that received something like 13,000 submissions, and they were able to sift out 3,500 papers, and that is just the main conference, 2 days. The other sides are things like workshops and so on. So it's a 7-day event that just contains papers. You can see this word cloud, the words language, the words model, the words large. You can see here large language models, data, learning, machine learning, neural networks, model, and so on and so forth. These are the words that are most common in those papers. Yeah. And it's not in the papers, but in the abstract. So you can imagine in the summaries of all the papers, the most common words are language, graph, diffusion, training, large model, and so on and so forth. So you can imagine, and a conference like this is an indicator of exactly what research is looking at. And this language, large language models stands out as the next big thing in the future. In the conference, it's common that conferences give awards, and there are 6 best paper awards. 4 of them were based on large language models. 1 of them on physics-inspired large language models. The other ones, 2 on data sets on large language models, and 1 best paper on large language models. So again, you can see, I'm just trying to motivate why you need to think about this topic, right? Why you might want to step back and say, okay, I'm going to go through this education, or I'm going to look into these papers. But the most interesting award that was given in this, the conference always gives an award called the Test of Time Award. So they tend to look back 10 years back, which was the best paper in that year. and how has it influenced research since then? And 10 years ago, apparently, NeurIPS in 2013 gave the best paper to a paper called Efficient Estimation of Word Representation in Vector Spaces. This was from Google Research, somebody called Mikolov, and you can see one of these guys was Jeff Dean, who is like a very big researcher in this field. Why am I talking about this paper? This paper was the first paper to introduce representation of words in natural language into mathematical vector spaces. The idea is that when you have things into mathematical vector spaces or mathematical spaces, then you can do computation. You can add things up, you can divide, you can multiply, you can concatenate, and so on and so forth. So this paper introduced techniques that can be used for learning high quality word vectors from huge data sets with billions of words and with millions of words in the vocabulary. So you can see here they introduced something called a continuous bag of words and the skipgram model. The continuous bag of words you can see on the left hand side, the CBOW has those words, weights of words, T2, T1, and all that. They are summed up and they're used to predict the word that is missing. So it's sort of like you remove a word and use the previous words to predict that word. What we call distributional semantics. Distributional semantics is a concept in natural language processing that comes from the fact that you will know a word by the company it keeps, right? So for example, if I said, I ate an apple in the morning, right? That the meaning of the word apple in that sentence is completely different from the word apple in this other sentence. Apple released iPhone 15 last December. So the word apple is the same, but the meaning is different because of the company of the word they have kept. And so these particular researchers thought, okay, why don't we use that information to be able to get meaning? And that is the first time we saw vectors of words coming into being. And because we are now able to represent words as vectors, then we are able to do larger computations. So this paper became a highlight because from this paper in 2013, there are a lot of work that came that now started to look at words as vectors and represent those. So in this paper, what they're doing is continuous bag of words. A bag of word is simply like words put together. There's no consideration of the position of the word, right? And it's a very rudimentary model. So it gets meaning based on did the words appear together rather than which word came first than the other. So the research extended this into positions and so on. And I'm going to discuss a few models that came after this that were able to, extend this. But you can see here that you guys will excuse me for just a minute. I'm just going to take 30 seconds, guys. Sorry. Right. Yeah. So as I was mentioning that this paper was a baseline for all that, and I've given reference here so that you can follow up later if you wanted to like get to the base of this. Right. From there, what happened is that now researchers thought, okay, how can we extend this kind of models? And the next logical thing that happened was to represent vectors such that the positions of words are understood also, instead of just that they appeared together, but more of which one came first, which one came second. And there came things like LSTMs, very handy, that is long short-term memory networks. And those are able to represent a sequence of words as they go and represent the meanings. But a major discovery that came in around 2014 was something called attention mechanism. Attention mechanism is a mechanism that says that let's only use, out of a sequence of items, let's only pay attention to the part of the sequence that is most meaningful, right? So if I said something like Dr. Muland gave a talk in a virtual talk to the University of Cape Coast in Ghana on whatever, and the idea is to relate only Dr. Muland with a talk in Cape Coast, right? The other texts become very not so relevant, right? So we want to make sure that the attention of Mulang and Cape Coast are so strengthened beyond the other texts. I hope I make sense. And so there's a paper by somebody called Banadu et al, which introduced that concept. And around 2015, people were doing that attention mechanism. But then in 2017, these are 2017 architecture, not 2022. In 2017, a researcher called Vaswani, again from Google, thought, let me use this attention in some way and stack several attention heads together such that it's able to represent more powerful concepts. And you can see the architecture. This is the architecture that broke the internet, if you want to speak so. Like, this is the, if you're not going to read anything else, please read this paper. This is the paper that broke the research in this area in 2017. Everything else that came after that was based on this. So you can see the concept here is, on the left, there are inputs, and you have to change those inputs into some embeddings. Embeddings means you want to represent them in some form of vectors, right? And again, on top of that, you can see there's positions, the position of the text. So you want to get the embedding of the text and then the position. Embeddings can be things like one-hot encoding, can be initialized as random vectors and so on and so forth, and then they're learned over time. So you want to push these embeddings at the beginning here, and together some with their positions. So the positions also have embeddings, and then you push that into some attention head. So multi-head attention, I mean, I can't go deeper into the mathematics given the time and all the complexity of that. The idea is, you want to, multi-head means there are several computations, maybe like 12. You know, the common architecture here was 12 different computations that are trying to add up vectors, the input vector with other words, and trying to find which ones are the most similar, if you like, or the most different, if you like. Depends on what you want to do. If you want to get the most different or the most similar or the most something orthogonal or whatever, you want to do that. So it pays attention based on your objective, right? Then you want to do that, and you move into a feed-forward neural network. Again, I'm sorry, there's some concept that I assumed, like neural networks, you probably have an idea of what a feed-forward is. Feed-forward is simply the computation forward in a neural network, right? Which is mostly takes the shape of weights times the input, right? That is what feed-forward is about. Then you add and normalize, and then you can see on the left-hand side, the computation on the left-hand side comes and joins the computation on the right-hand side, right? So you can see now on the output embeddings, again, we add with positions, and then you can see here, again, the same architecture, multi-head attention, but this is masked. Masked means that the word we want to predict has been removed, so we want to predict that word. That's what it means, masked. Then now, so the context comes and joins here, and then we compute. The softmax is the classification, right? So we classify among many words which word we want to output, okay? Now, on the right-hand side, you see things called query, key, and value pairs. So you can see the query is matched with the key, and they form one context. you want to think about a translation system, for example. You want to translate from English to, is it Asante or Ashanti? One of those. You want to translate to that. So you want to get the sentence together with the English sentence, which is the query, and the Asante sentence that is the key, and you want to match them up using this attention architecture until you classify. But then you want to multiply again that with the value, and the value will always be the key. So you want to multiply with the key. So this value now, you can see there are several sentences. Maybe you want to match with Asante to be able to predict the actual output, right? So yeah, so this is the architecture of that. And you can see on the right-hand side, again, you have value, key, and query. Now it's just the reverse of that. So you can see dot product, attention. Basically, you're multiplying vector with another vector to be able to see how close they are. And then you can concatenate all these attention heads, and then you classify. Yeah, so that's a shallow view of that, or maybe a summary of that architecture. But this architecture is what we call the transformer architecture. The transformer architecture is the mathematical or computational model that came, and everything else that came after that. There are right now maybe thousands of models that came after that. Even ChatGPT or GPT is based on what we call the transformer architecture. So everybody has this. What came next in 2018 is that, again, researchers from from Google came up with another model called the BART. And what Delvin and his team at Google were doing is to now say, since we have this thing that is very computationally sound, let's blow it up. Let's have so many layers of this such that it's able to capture a lot of representations, and those representations can then now be used in downstream, what we call downstream tasks, in predicting other tasks, okay? And that's what the BART did. So the BART architecture is based on that. You can see these attention layers, T. So at the base of it is just encoding. The encoding layers looks like this. You can see when a word comes, the word 0, word 1, word 2, word 3, word 4. These are embeddings. E stands for embedding, right? Word 1, word 2, word 3, word 4, and so on. At the second level, we add the word embedding with, or the token embedding with what we call here the segment embedding. So the segment is like a part of the sentence that is relevant. For example, you want to use like three words as a segment, or maybe where there's a comma, you consider that as a segment. So when you consider that, you are getting like, what is the distribution of that word based on its neighbors, basically, right? And then the token embedding. So this is positional embedding, then token embedding, right? Position is simply just in this sentence, for example, if you said something like the dollar has really gained against, maybe, for example, the Kenya shilling, for example, right? So you can take the whole of that as a segment and you give it embedding. So all this will be equal embedding. The position, the word dollar is at position 1, has is at position 2, and so on. So they'll have different embeddings, and the tokens, dollar is a different embedding, and so on and so forth. So you add this up to get one single embedding, and use that for computation. You pass them through the attention layers and you get what you want to predict. So the BART was a masked language model, to mean that it was like it took the whole of Wikipedia and was able to like mask some of the words, and those were the ones that it was trained to predict. The things that during that prediction, or during the learning of that, they're able to capture what we call emergent properties. Emergent properties are things like, it was able to get meanings of words that were not even for the same task that it was trained for. Yeah, so that then now you can use BART for identifying, for example, that the word Africa is a named entity, is a continent, for example. That was emergent. The idea was to predict words that are masked, but there are so many other things that came up with it. So it was able to be applied in things like question answering, like Squad is a question answering task, named entity recognition, like you can tell a person from these embeddings, and so on and so forth. What followed was a mirage of other models that are based on this kind of models. I'm sorry, Steve. It looks like I have 7 minutes, but yeah, I'm gonna try to push this through. I don't know whether there's.
No, you can go if you want to use.
Okay, good. Yeah, so I'm gonna try to summarize, but let's see. So what followed is that other researchers now came up with other models which are related to that. Like, for example, GPT, it was simply GPT before. In 2018, it came out. I think 2017. GPT-2 came out, followed that. What we have as ChatGPT is GPT 3.5. And I think OpenAI has released GPT-4, which is not open source at all. And then, so BART came, and ExcelNet actually did better than BART. And then there's Robata, which came from Facebook, and GPT and all, and so on and so forth. You're aware of things like Llama, and maybe I'll mention that as we go. But out of all this, there are two major objectives. For mathematicians, there are two major objectives that are looked at in this. One of them is called the autoregressive, and then the autoencoding. I've explained a bit of the autoencoding. You can see the second one, the AE one, is the autoencoding. It takes the log probability of a given word or text given a corrupted text. So you can see this is the probability of some text given corrupted text. Corrupting can be things like masking a word, removing a word from the sentence and giving it some funny whatever. So this is just the log loss, the log probability of a given word given that corrupted sentence, right? So it encodes, it automatically encodes the meaning of the word. And this is just an expansion of that. You can probably take a deeper look. The paper that I got these equations from is ExcelNet 2020 paper, right? The other version of it is the autoregressive. The autoregressive gets the log probability again still of a word given all previous words. So this is trained to predict the next word in a sequence, right? The next item in the sequence. This one is trained to predict a corrupted word, right? So you can see there are different objectives, but pretty close. GPT, what we now have as ChatGPT, is an objective that uses this auto-regressive approach. BART and many other ancestors, descendants are using this particular objective. I cannot tell you which one is better or the other, but some researchers have tried to combine both objectives into one thing, like the ExcelNet. If you read this paper, you'll get the meaning, okay? Now we come to the ChatGPT, because it is the model that has really blown this thing up and has caused a lot of trouble or squabble in the tech space. Because what I will tell you for free is that Google has been doing this research for so long. They really had probably even better models, but they had not thought of releasing it in the way that ChatGPT, OpenAI did it. And OpenAI was boom and go, and has created a discussion and competition. You can see that Microsoft sort of just shut down their research division because they were not able to come up with such a thing, and adopted the OpenAI model. Actually, they've even brought in Sam Altman, who was the research head at OpenAI, right? So it's been the news, it's been so rampant, it's now famous, and you can imagine that it had millions of users within the first month of release, right? So that is natural language processing and how the research has developed over time until we have gotten to a point where we have ChatGPT. Yeah. So you want to think about the paper in 2013 by Mikolov et al. which did representation of distributions, distribution representation of words into vector spaces. Then you want to think about the attention mechanism that came in 2014-15 by Badenau et al. Then you want to think about how the transformer model was able to use attention heads, like so many attention heads, to be able to represent that. Then the next step was how this attention mechanism the paper actually in 2017 by Vaswani was called Attention All You Need. All you need is attention, right? So that attention paper has been blown up into a model called BART, which then has the characteristics of a foundation model because it was able to learn a lot of good vector spaces that can then be used in some other tasks, what we call downstream tasks. And the emergent properties that came with the training of that is what now people are using as foundation models or LLMs. From there, there's been a mashup of things that has led into this ChatGPT, into many more. On the other side, now people are thinking, how can we do the same for vision? Because research happens that in one domain, if things are working so well, people want to transfer that into another domain. And you can see in vision, what we call the variational autoencoders came up. I'm not so sure the year this came in. It was actually a language model for translation, yeah, for encoding English, and on the right side, you decode it into Asante, for example, right? And so on. But it works well for images as well, okay? You can see how it works, its probabilities, and so on and so forth. And we later on came up with what we call the generative adversarial networks. And on the one side, you can see we have the generator, and the other side, we have the discriminator, and so on. Then recently we have had what we call the diffusion models, or what we call the stable diffusion. The diffusion models are very powerful. They beat the other two. How it works is that it's able to take an image or a vision or a video, and then learn the space. Again, it's all mathematical. Underlying, you can see the patterns. And for you to understand patterns, you'll have to understand vectors and so on. So it takes an image, and this image, it's gonna add noise to that image until it becomes white noise, right? Then it starts reversing the process, right? To mean that now it conditions based on the white image and targets to get to the original space. And in that process, because it's starting now from the white noise, it's able to, it doesn't really get to the exact image, but to rather the space where the image was. And once you're in the space where it was, you can draw several samples that are similar to the original. So the idea is you want to get as many samples as possible. There's a paper by, is it Microsoft? No, OpenAI actually, that came some 2021, I think, called DAL-E. DAL-E is the paper again that broke the internet in terms of people getting their hands on things. And it's the one that is being used now. The model is the one that is being used to generate fake images, fake videos, and stuff like this. It's a vision model that is able to understand the space where a given image sat. And no, this is actually white space. And it's now, this is the reverse. What I have here is just the reverse process, okay? What happens that we had an image, and that image was taken to white noise. So CT is some white noise. Now we are reversing it back to get that. So you can see the probability of CT minus 1 given some, what is that G? I forget, but then the vector for the CT1, okay? So then that's how it works. So the diffusion process has been applied in molecules. Again, I added the what is it called? The objective here, so that you are able to follow. If you want, looking for a paper that is talking about this kind of process, we have a paper called a geometric conformation diffusion model for molecular generation. So this is mostly used for molecules here, but it works for images, okay? I think mathematicians, you guys will be able to understand. Yeah, so these are some of the examples of molecules that are generated by the model. You can see on the right-hand side, we have the original, on the left-hand side, we have the original image. And on the right-hand side, after the model has learned, it can generate as many molecule structures that are similar to the original one, right? So there are several variations of that. But what are some of the limitations of large language models? So recently, there's a lot that has come up about, of course, research has to extend this, but there are limitations of these models. One of them being hallucination. You can see here, I asked ChatGPT who is the first African to receive a Nobel Prize, and it gave me the name of a German. Apparently, this German was researching in Africa and stayed so much in Africa. He's called Albert Schweitzer. If I did not know some German, I may have taken that as the answer. Or if some American was asking this, doesn't know African names, they would have taken that as the answer. But I asked the same question again, and because now I gave it context, it was able to quickly correct itself. I says, I apologize, these are confusion, and now Albert Luthuli came up. But then I asked this the question again in a different format. The first African to win, the first African Nobel laureate, and it went back to Albert Schweitzer again. So you can see, because these large language models are trained in such a huge amount of contextual data, it learns such huge representations that sometimes it gets confused in representation, right? Another answer is, for example, who is the governor of Rivers State in Nigeria? And you can see that Nigeria recently had some elections, I think 2 years ago, I think 1 year or 2 ago. And you can see that it's not able to tell me that, yeah? It told me up to 2022, there was Nyesom Wike, but there is a new governor, apparently, of Rivers State, Nigeria, right? If I ask you, for example, which LLM was created in Africa, it's not able to, it's gonna give me some facts it thinks is right, but it can't tell me where it got that information. So these three major problems people are facing, such as are facing in large language models, and people are looking at how they can use other techniques to help solve this provenance issue, hallucination, and sort of like update problem of large language models. The other challenges we have with large language models are things to do with the cost of training, right? The cost of training these models, because these models are so big, they learn on such a big amount of data. Just keeping this data in one computer may be a problem. And probably this is why maybe in Africa, we may not be able to have the compute power or the capability to do this. For example, ChatGPT was a 175 billion parameters. Yeah, parameters, I think you people will understand parameters from statistics, like the model of a straight line y is equals to mx plus c. The parameter over there will be the m, right? That will be a single parameter, right? But now you can imagine you're training a model that has 175 billion parameters. That's a huge model. Sometimes takes months to train this. It will take huge amounts of compute. The thing with Google is that they have such big, powerful machines to do this. So they just experiment every day. But with us, we probably need another approach to do that. Google released, after GPT released their, OpenAI released their GPT 3.5, Google quickly released another model called BARD. And BARD is a 137 billion parameters. The difference is not so big, but a bit smaller. It worked on data. 12% of the training data came from Common Crawl. The same to GPT. Another 12.5 came from Wikipedia. Again, came the same to GPT, and so on. So this is how GPT was trained. This is how Google Bard was trained. But we have to say that there are quite a number of, quite an amount of data that was not released, was not from open source. Okay. What I'm meant to have here in this blank space is what we call Llama, the Llama model. The Llama model was released by Facebook, or what we now call, what is it called? Meta AI. And it's an array of models ranging from 7 billion to 65 billion parameters. So you can see even the largest model of Llama is just half, or not even half, a fraction of the others, right? And it's claimed in their paper that the 13 billion, the Llama 13 billion model is able to perform as good as these other models. So the idea about Llama is that it's trying to reduce the size of the computation, the size of the parameters, but they, of course, their modeling structure is different. So probably if you want to go into this space again, you might want to look at Llama and try to play around with that, because it's completely open source, okay? The other cost configuration is to do with what we call running time and training time, okay? So, for example, if I was to query ChatGPT, okay? Here, I borrowed this from a presentation I had at the University of Lagos. So I'm sorry, I don't have University of Cape Coast here, but yeah, you'll get the point that if you queried ChatGPT on this kind of small query, it will give you this answer, which is very correct, but it will take 2.5 seconds to do that. If you asked, what is it called? Google, now this is Google search. Remember that Google search is powered by all these things, powered by some large language model, powered by some other technology called the knowledge graph and so on. Google gives you even a better output, including images of the person who founded the university and so on. And you can see it takes 0.5 seconds. Now, the third technology here is called the knowledge graph. The knowledge graph is a representation of, content, or what we call text or entities in a graph format, right? Such that it's more like triples. We have the head, the relation, and the tail. If I was to represent the talk today as having been organized by Dr. Stephen, I would say Stephen is the head, organize the relation, this series on AI, right? So we have those two entities and the relation. So that is the model that is used to represent in knowledge graph. And some common open knowledge graphs are Wikidata and DBpedia. Now, I can get the same information that I was given by the large language model and Google here from the knowledge graph using what we call a query. This is what we call a Sparkle query. The knowledge graph gives a quicker answer, not really well formatted like the other two, but it gives the answer all the same, but takes 0.26 seconds to do it. So you can see the knowledge graph is faster. The others are a bit slower, right? So you can see here, in terms of cost consideration, OpenAI, ChatGPT takes 5 seconds. Google, the search engine, takes 0.5 seconds, albeit it gives better output. And the knowledge graph takes 0.2 seconds. Yeah. Now, what are we saying? That sometimes it's better to use other tools to do some tasks, right? As opposed to always thinking LLMs will do everything, okay? In terms of cost and all that. But more so, we are saying that we can combine the power of the two, right? There's a whole field called graph ML, or graph machine learning, which has been extended into representing knowledge graphs into vector spaces, right? So if you can have the knowledge graph into vector spaces, you can use them as context for your LLM, or even combine both LLM and the knowledge graph into something more powerful. So that is a direction that is being explored by a lot of researchers in this field. But the point is that never use a gun to kill a mosquito. If you can quickly do something and represent something without having to use the big knowledge graphs that will cost you so much compute and take longer to answer questions, then you're better off using other technologies. But LLMs and foundation models are very powerful, and we cannot ignore them right now. The other area that people are looking at is how do we reduce the training time, the training requirements of LLMs, so that then they are able to fit into maybe, for example, edge devices. They're able to use less resources. Remember that there's a lot of also factors about resource utilization and just how preservative to the environment are these models gonna be. So because every time you use power, every time you use resources, you are essentially affecting the environment. So they are not suitable in all scenarios. They may be too expensive in some cases. They need help from time to time. This paper is a paper I did in 2021 that was trying to combine knowledge graphs. On the right-hand side, you can see Wikidata and a large language model. In this context, we have Roberta and ExcelNet. And from this paper, the resounding findings was that the combination of knowledge graphs as context to power, because this is just fine-tuning process, to power a fine-tuning process works better than even a pre-trained model. So there's a lot of power in combining this and the other, okay? Other considerations that you want to think about are things like expressivity, scalability, multimodality, like how can you combine images and text all together, memory capacity, and so on. In terms of data, how can we scale data? How can we have quality data? There was a story when they released ChatGPT that they hired some Kenyans to help them label their data, and sort of like the pay that they gave the Kenyans was just a fraction of what they would naturally give in the US. And there was a lot of stories. If you read the Time magazine or the Time in the US, they reported this, and that goes into things like ethical considerations and so on. But it's difficult to get quality data and integrate data from the several sources. So those are considerations for this. There are considerations for evaluation. There are considerations for adaptation. All these are sort of can be considered as research, open research questions, right? If you wanted to go into those. So, like I've said, you can now combine the LLM with knowledge graphs to be more powerful, right? There are several researchers working in this space. And yeah, I think it's something you can easily get papers on if you were to follow. Some emerging fields from this area, we have retrieval augmented generation, because as I've discussed this, you have seen the gist of it is about generation. You're either generating what has been corrupted or you're generating the next unknown, right? So how can you use retrieval? So retrieval has to do with, you have a knowledge base somewhere or a knowledge graph somewhere, and you're using that to augment your large language model. An authority in this area called Andrew Ng, I don't know how to pronounce his second name or his surname. I don't know whether it's Ng or Ng or whatever it is, but it's Andrew Ng who works with Google. Recently gave on LinkedIn a proposition on large vision models, right? So we want to copy the same for large language model, from large language models into large vision models. The challenge with computer vision is that a cat is just a cat, right? So it's difficult to train something on a cat and transfer that into MRI scans, for example, right? Or CT scans. Those are apples and oranges, they cannot do. as opposed to, for example, if you were to train something on Wikipedia text and use that in some Ghanaian legal text. You see, text is very close, so it's easier to transfer language trained models from one domain to another than vision models. So large vision models will have to do with domain-specific training. For example, you have medical images and it only transferred from maybe, for example, European labs to African labs, but they have to be medical images, for example. Multimodal foundation model is about combining, for example, text, sound, audio, all these representations, right, into one single model that can be able to generate so many things. So what is our role, right? What's our role in all this? We definitely might not have the clusters, the big clusters like Google has what we call the TPUs, and they just can experiment anyhow. But what we can do is to start collecting data and curating that data and starting to reuse the models, because the idea about LLMs is that the model should be reusable, right? They are available and they should be reusable. And for example, if you went for the Llama model, a good source for large language models is a website or a repository on GitHub called Hugging Face. Okay, Hugging Face is a company that started in around 2018, and they have really grown, and they have all these models in some repository on GitHub, and you can choose whichever model you want to do. Okay, so you can reuse those models as long as you think it's suitable for your task, and do a process called fine-tuning. Fine-tuning is basically what I talked about, those vector representations. You take those representations and now do extra computation on top of that, maybe like add a classifier, add a regression head or something like that, then use that to predict things. But we must have our own data. That's mandatory, that's paramount. We cannot use these things if we don't have data. So for me, I think the obstacle or the pain point for Africa context about how quickly can we collect data and curate that, so that then we are able to enhance, harness the power of these models. So in conclusion, large language models, or what we call foundation models, are here to stay, and it's high time that we all got on board. And how to get on board again is about collecting data, knowing where these models exist. And I've just mentioned Hugging Face is a good starting point. There are even courses that teach on how to use that, and then train on contextualized data, so that then we have the differential, right? I met a researcher, again, I think, Steve, that was the time we were in Rwanda. There was this Egyptian researcher who works in the University of Liverpool, and we had a discussion with him, and he was talking about how they are looking to do some models for the like CT scan models for Africa, some hospitals in Africa, but there's no data. So they started by sort of doing transfer learning of the models they have in Europe, and they wanted to transfer that to Africa. The challenge is that the equipment that has been used in Liverpool is completely a bit advanced, let's say, and the quality of those images are way better than the images they will probably fetch from this. Some very few hospitals probably have those kind of high-tech whatever, and so they don't have enough data for the same. So if you're gonna, and of course, yeah, so that means that the transfer learning they did was just basic. They got something like performance like 0.4, which is not good enough. So they have to actually look to get data from this Africa context, for example. Yeah, then consider augmenting this with other techniques like knowledge graph and so on and so forth. And I think that marks the end of my presentation.
All right, thank you very much, Milan. So if you have any question, please You can write it in the chat, or you can unmute yourself and then you ask your question. Or you can raise your hands. You can raise your hands up, and then I'll let you go ahead and ask your question. Anyone with any question? You didn't understand it?
Normally they say that if there are no questions, it was a boring talk. There's a chat.
Yeah, please, I have a follow-up. Can I continue?
Yeah, go ahead. Yeah.
All right, thank you very much. That was insightful. Now, my second question is, I read somewhere that general purpose search engines have this problem of only searching and indexing surface web. They are not able to get into what is referred to as the deep web. How can the use of these large language models remedy some of these issues?
Come again, the first part I didn't quite get that the search engines are not able to
They're not able to crawl
Mhm.
the deep web, and so they are only able to index the surface web. And I read somewhere that if you look at the capacity of the deep web, it is about 60% of what is able to keep relevant information as opposed to the surface web. And so I read that there are interventions. People are trying to look at how they can bridge this gap in getting more data, as it were, to be crawled. And so I'm asking, with this intervention, with these LLMs, how do you think they are able to solve this issue of just crawlers able to access the surface web, which are text and data that are not subscribed, that are generally on the web, as opposed to those that are in the deep web? Thank you.
I won't claim that I have an answer, a direct answer for you in this question, because I'm not into search per se, but what I would think is, if you can represent, right, whatever form, the only challenge will be the computational power required and just the amount of parameters you'll need for that. But if you can represent whatever amount of text is in that deep web, or whatever amount of content that is in that deep web, into an LLM, so you have an encoding of all that, and you have that as a representation. And right now, LLMs are generators, so there's an aspect of generative AI as well. Then you can sort of like push out content from the LLM that has encoded that non-reachable part of the web, as you would put it, and use that as augmentation for what search would do. What I imagine is that something like Google search engine is already quite extensive, right, in terms of reaching the content they will probably want to reach. And if there is a gap that remains to be bridged, I think it's a matter of representation of that particular content. The question is, will we ever have computation large enough to be able to capture all that web, right? I think we might never get there, because the thing is, the rate at which content is being generated online right now is way faster than any technology can be able to catch up with, right? And it will only get more and more as we move forward. So sometimes about cost benefit analysis, and you want to say, what level do you want to get? That's enough representation of what people normally will search and try to find, right? But certainly, if you can push all that web into a large language model, the aim is to have representations of those, then we can generate content from that. Then I think we can bridge the gap a little. I think there was a question on the chat as well. Question about GNNs, right? Graph neural networks. Yeah.
Yes, there's a question that I would like to know. I would like to know if there is a difference between GNN and graph representational learning.
Yeah.
And then someone is also asking, what are the, in terms of research areas, could you expound on technical skills required to do research in these areas?
Okay, good. So good. The question from Joe Ajay. GNN's graph neural networks is already graph representational learning, right? It's, I think, the first models that came out to capture sort of like vectors of a given graph, right? But if you think about graph representation learning, the tasks that exist in graph representation there has to do with, well, in respect to knowledge graph, right? Has to do with knowledge graph completion and link prediction, right? Now, you don't necessarily need to have a GNN per se to do that. You want to sort of have an objective that is able to link the tail entity with the head entity, right? So on one side, we have the completion task, which tries to predict what is the tail given a head and a relation, right? So if you had something like Albert Einstein studied in, went to, or maybe attended ETH Zurich, for example, right? That's a fact. So now we have Zurich, ETH Zurich and Albert Einstein as the two different entities, and we have the relation that exists in between, right? So if I was given Albert Einstein as the head entity and went to school or attended there, right? I want to predict what is the tail entity. I'm talking about graph completion. But if I was given ETH Zurich and Albert Einstein in some graph existing, I want to get the connection, I'll be looking for the relation attended or went to school to, whatever this is. So there are several ways of doing that representation. There's a whole research area called knowledge graph embedding, which came to existence in 2013 as well, I think, with a model called, well, not 2013, there is 2011. Researchers came up with Rascal, something like that, that represents a knowledge graph into vectors, basically, and then can do those additions, computation, and so on. So basically, if you can have an objective that looks like the head plus the relation should give you the tail, something like this. And then you want to minimize an objective that has something to do with that. Then we came to things like Trans-E, translational embedding, which sort of talks about translation of entities and relations into the vector space of the tail entity, something like that. And there's a lot of again representational learning in that space. We had Trans-R, we have Torus-E. There's a whole lot of models there that has grown into things like translations into vector spaces, mappings from vector space to this and the other. The one paper that I worked on in 2022 really, had to do with using Hopf vibration. There's a in mathematics. I think you guys are better mathematician than myself, but Hopf came up with what do we call Hawk vibration is sort of like a mapping of a point in 3D space into, no, actually it's the reverse of it. Yeah, mapping of a point from 3D space into like a cycle or a sphere from 3D space into a point, right, in 2D. And we were trying to look at how do we reverse that process from 2D into 3D, because when you have things in 3D, then you have better expressivity. You can represent a lot of things. So if you think about knowledge graph, you want to have an angle on the tail, another angle on the head, and another angle of the relation. It's better to have like a sphere more than a point, right? So all these methods have been worked on in terms of graph representation. There's a guy called Michael Galkin, who happened to have been my former colleague in PhD, nowadays work with Intel Labs. It's a guy you can follow if you wanted to do graph representation learning, right? But GNN are very much in that space, right? It's graph representation, right? Yeah, I think that's what I can say there. If you wanted to really get deeper into this, I would suggest you look for somebody called Michael Galkin of Intel Labs. He did his postdoc with Miller, and they form a team and do this sort of blog posts on the best papers in that space. And I think yesterday he was doing a presentation on some paper they have got accepted at ICLR. It's some space you should follow and do that, but the difference is not much. GNN is part of graph representation learning. In terms of what skills do you need to get into research in this space, I think you need research skills, right? Research skill is about being able to read a paper, being able to understand the method in the paper, and being able to sort of synthesize the experiments and the output of that paper. Those are skills that we get at master's level in general and at PhD level as well. The other thing is, of course, you will need some technical skills like programming skills. The areas that you want to look at are deep learning, frameworks for deep learning like PyTorch and TensorFlow. Because ultimately, even as you read the paper, you want to look at the GitHub code and implement that and be able to extend the same. You need some software engineering skills, because right now, almost all code is done. How research now combines software engineering, and because you want to train this in large clusters, you may need to split a model into several sub-models and then combine them later. That has to do with software engineering, distributed training, and so on and so forth. There's aspects of continuous integration, continuous development, CI/CD, and so on. All that shebang. But the most important thing is to be able to understand what is in this field, and that's what I've just discussed. The whole presentation was about what is what in this field, right? Where did we start and where are we going? So you know which papers to start reading from. And if you read that and be able to synthesize that and be able to write some code, I think you're good. The idea is, even myself, I'm still learning a lot of things, right? But you need to have an anchor, be able to say, look, I'm gonna start with GNNs, for example, drill down on that, and be able to write some codes in that space as you expand forward. Or I'm gonna do LLMs, and you want to start with like the basics of that. Start with the Mikolov paper, for example, or maybe just start with the Llama, and be able to write that code and be able to run it and train a few things, then move forward. But the most important skill that you need is passion, right? You need to love what you're doing. You need to love to say, okay, I really love and I'm enjoying training these models, and so on and so forth. So all the other skills like analytical skills, problem-solving skills, those ones you can develop as you go, but you need to love it. You need to love that, I love the mathematics behind it, and I love this and the other, and so on. Yeah. Steve, someone also asks about how are LLMs used in healthcare? Oh, okay. LLMs in healthcare, there's a lot that can be done there. There's some field called clinical NLP, right? If you think about doctors writing diagnosis, symptoms, and so on and so forth, there's a lot of literature, researchers in medical domain writing papers on all that. We can take all that literature and electronic health records and be able to train an LLM to understand the relationship between a given disease with a given medication and other diseases, the relationship between, for example, a flu and COVID, they are related in one way or another. Yeah, and so on and so forth. So then a doctor can ask questions and get helped in diagnosis, or a patient can quickly, get help in accessing medication, and so on and so forth. So that is NLP, or clinical NLP. The other side is, if you think about what's happening in the background, discovering of drugs, it's a whole clinical trials process that takes so long, like 13 years sometimes, with monkeys being jabbed here and there, and maybe rats in the lab. If you think about that process, you can use LLMs, or, well, this one might not be exactly LLM, but more of foundation models, which are based on concept from LLMs. If I had the structure of the molecule that was used to cure SARS-CoV-2, for example, right? Then I can use that representation to generate so many molecules. One of them might be the answer to COVID-19. For example, if by the time COVID-19 was breaking out, and we realize that the structure of it or the symptoms of the same are similar to SARS-CoV, I can go back and use a foundation model that was trained on SARS-CoV medication, and use that to generate for me molecules that can be used to generate drugs for the new particular disease. Something like this. So, for example, I've been working on using diffusion models as foundation models for generating new drug molecules, novel drug molecules. So there's a number of things there, right? There's so many things. You think about biomarkers, right, for diseases, right? And the process of clinical trials, how it comes into endpoints, and so on and so forth. We can do that process via simulation if we had a foundation model that represents the whole process into vector spaces, right? And do computations there and be able to predict a given endpoint. Remember that we can predict also like adherence, drug adherence. There's so much in that space in healthcare that I can't talk all of them, but I think I hope I have motivated or maybe triggered some thought in your mind about how these things can be used in healthcare, right? Yeah. Yeah. Steve, I think probably I'll maybe shift into some other task now. This was really